In this video, we're going to be taking a quick look at friction. And friction is probably something that you've already seen before, you've worked problems through before in your physics class. So friction is just this idea that when two surfaces are up against each other, they cause forces to act between them from them rubbing together. And this is our friction force. So we often see it, say, if we have a box laying on the ground and I have someone pulling on that box, then I have a friction force between the box and the ground here. A friction force is created in the opposite direction of whichever way I'm pulling the box, right? So I have this friction force created because this box has some weight that is causing a normal force on the ground, and that normal force becomes our relationship to the frictional force. So we've probably seen this equation in Physics 1 already, this friction F equals mu, the Greek symbol mu, mu is mu. Our frictional force, static or kinetic coefficients of friction, right? Mu is the coefficient of friction times the normal force. This is our friction equation that we've gotten used to seeing probably in physics, and we're going to be using it again here, but using some of our knowledge of statics to apply this equation. So our equilibrium equations can now come into play, because we can look at this and we can say, okay, sure, I can determine what the frictional force is, but what does that actually mean for what's happening to the box, right? There are three basic things that could be happening to our box. One is that the box could be in equilibrium, right? It could be in equilibrium and not move. Be in equilibrium and does not move. So I'm pulling on this box, but the frictional force is stronger than the force pulling it, so the box does not move, right? Stays exactly as it is in the picture. My secondary case could be that my pull is so strong that now it does move, right? It's slipping. It's slipping against that friction and it begins to move. So it does move, and we call this slip, right? It slips against the friction on the floor. It does, in fact, start to move. And then our third scenario, and this is kind of a new one that we could only do knowing our equilibrium equations, is that the box may also begin to tip over, right? We've seen this before, someone dragging a box or pushing a box along a floor, and then all of a sudden that box starts to take a tumble, right? So the third condition we could have is that the box starts to tip. And the key with knowing whether a box is tipping or not is our moment formula, right? Because a tipping is a rotational sensation, right? It's a rotational movement, which is exactly what our moment is. Our moment is a desire to rotate. So tipping comes from our moment equation. We can determine whether something is tipping or not. So the way that we check whether a box is stationary, slipping, or tipping is through our equilibrium equations. So we can use our equilibrium equations to find the actual frictional force. So friction actual comes from our equilibrium equations. Whereas this formula here gives us our max theoretical friction. So if our actual friction is less than the maximum, then the theoretical maximum, it means it's not slipping, right? So in equilibrium, our actual frictional force is less than the maximum that we're calculating. Theoretical. Whereas in our slip condition, that means that we have exceeded the maximum. The actual frictional force is greater than that theoretical maximum created by this equation. And finally, we have the tipping, and this is more of a center of gravity situation. So it's when we have our box, we calculate our moment. Here's our normal force. We have this distance x between the normal force and the center of gravity. Wherever this normal force is located determines if the box is tipping. Because if the normal force is located all the way to the right, all the way to this far corner of the box, if that normal force starts coming outside of the box, that's when we're going to see this rotational movement, right? The center of gravity moving it so that the normal force is now pushing at the very corner causes that tipping sensation. So let's work through a couple of problems to see how this works. In this example, I'm given a box. It says if the 20 kilogram box is in equilibrium, given this static coefficient of friction, determine if it is in equilibrium, right? So we want to know, is it slipping or not? Is the friction actual greater than or less than our friction max? So we're going to need to calculate both of those values. And the first thing we always do in any situation in statics really is going to be our free body diagram. So here I'll draw my box body. I have this 80 Newton applied force that's acting at a 30-degree angle on my box. Then I have the weight of the box acting at the very center, where it gave me the mass is 20 kilograms, so I multiply by 9.8 to get that value in, right, the force value of my weight. Then, of course, I have to do my normal forces and my frictional forces. And it's important to note here that our normal force is not going to be directly beneath that weight. It might be offset, right? And under the case that it's tipping, it's going to be in the corner, and we don't know exactly where this normal force is shifted because of the applied load. So we're going to just arbitrarily put this normal force at some distance x away from the center of gravity, away from where that weight force is being applied. So I have my normal force here. And then, of course, my frictional force always opposes the load, always goes in the opposite direction to my load. My load is 80 to the right, so my friction is going to be pointing to the left. Right, and it's at that same point where we have the normal force applied, because those are related, right? So to find our F actual, our actual frictional force that this thing is experiencing, we're going to use our equilibrium equation, which is fairly straightforward, right? We just do our summation of our forces in the x direction, and that gives us our frictional force. Right, so sum of forces in the x direction is going to give me my negative friction force plus the x component of that 80 Newton applied force. So that's 80 times, this is the cosine of 30. So easy enough. F actual equals 80 cosine 30, which is about 69.3 newtons when I plug that into a calculator. So now I have F actual. Let's go ahead and compare it to our theoretical frictional maximum. And that comes from our formula. Friction equals mu times n. So our static coefficient of friction multiplied by the normal force. Now, of course, I don't actually know the normal force yet. I haven't found it. I gave me 0.3 as my coefficient of friction, but I don't know the normal force. So in order to find that normal force, I'm again going to apply my equilibrium equations. Sum of forces in the y direction this time is going to be my normal force minus my weight, is that 20 times 9.8, minus the y component now of that 80 Newton applied force, so 80 sine 30, gives me a normal force of 236.2 newtons. So I can take this, plug that into my formula, plug in my 0.3 for mu, and I will get 0.3 times 236.2, meaning that my F max before slipping, that's the maximum before it starts to slip, is going to be 70.9 newtons. So now that I know the theoretical maximum before slipping and I know the actual, I can see that my F actual is less than the max before slipping. So that means that my box is not slipping. So yes, it's in equilibrium. Yes, in equilibrium, not slipping. Right? If it were slipping, then we would have some F actual that was greater than 70.9. Now, I will say it's very, very close to slipping, right? You only need, only 1 or 2 more newtons before that thing starts to slip on the ground. But at this very moment in time, in this exact situation, it's not slipping yet. But now how do we determine if it's tipping, right? So this would be our answer that yes, it's in equilibrium, it's not slipping, but let's confirm the other case that it is not tipping, right? How do we find out if it's going to tip? We can see we've already used 2 of our 3 equilibrium equations that we know in 2D, right? Our sum of x forces and our sum of y forces. So logically, there's really only one more place we can take this, and that's to our moment equation. Right? We have our moment equilibrium equation that we haven't used yet. So I'll go ahead, make some room here. And let's use my moment equation. Now the real question is, where do I take my moment about? What point makes the most sense to take a moment about? And it's always going to be about, well, I shouldn't say always. It's going to be about, typically, it's going to be about this center line where the weight is going through. You want to do it where your center of gravity is. So where your center of gravity is, so that way you can capture where this normal force is hitting. Because we want to find out if this x distance falls within the box or if it's greater than the box, right? We want to know if it's hitting that corner. This x distance is really the thing that we're interested in. So we want to make sure that that's captured in there with our normal force. So here we're going to take this right about here because that's going to eliminate my frictional force as part of the component of this. Instead, I'm only going to care about my 80 Newton applied force and the normal force. If I take a moment, let's call this O. A moment about O equals 0. Go ahead and do my moment. I'm going to have my x and y components of this, and then my normal force. So that'll be my 80 sine 30 times its distance away. This point is halfway. Then this distance here is 0.4 minus 80 cosine 30 times its distance away is 0.2. And then finally, plus my normal force times x. Now my normal force, I know. We already found that earlier in our problem. We found that the normal force was 236.2. So that's the value that we're going to be using, and we're solving for the x value. That's what we care about. We care about that x location. And here, when I type all this into my calculator, I get that x is negative 0.009 meters. Right? So 9 millimeters to the left 9 millimeters to the left of the center of gravity. So my normal force is actually being applied like right there. Just barely to the left of the center of gravity. So it is not tipping. We would know that it was tipping if my x value was greater than 0.4 in either direction, because that would mean it would be outside the box over here, right? Or outside the box over here, and then my thing would begin to tip. This is a situation you see a lot more on like an inclined plane, typically, but here we don't have any tipping. It would require a great amount of force to start to tip this box. So no tipping. That's it. So it is in equilibrium, it's not slipping, and it's not tipping. And those are usually the things that we're checking for in these types of problems. Let's look at a different kind of example. So in this example, I'm given a vending machine that's on the back of a dump truck, and we know from experiments and from past results in real life that we notice the vending machine begins slipping off the dump truck when the dump truck is angled at 25 degrees. So we want to know what the static coefficient of friction is between the vending machine and the bed of that truck, the floor of that truck. So we're told that the slipping begins right at that 25 degree. So even if you aren't sure what to do, if you don't know how to approach a problem like this, always we're going to want to start with a free body diagram and then see where you can go with your equilibrium equation, right? Our sum of y forces, sum of x forces, and our moments. See if those can take you anywhere in trying to find our coefficient of friction here, our mu. So I'll go ahead and do that. Let's draw a free body diagram for this guy. I've got my vending machine. That's not quite as nice as the one that was already drawn there. But I've got my vending machine. It has a weight acting on the center. Notice that it's acting still vertically down, even though my machine is tilted. And then I have a normal force and a frictional force. Again, the weight is acting downwards to the right, so the friction will be acting to the left, opposite direction of wherever the force is. Because there isn't actually an applied force, it's the self-weight of the object that is causing this friction, causing the slipping, and possibly tipping. So this is our full free body diagram for this. And we'll notice that they actually didn't give us a weight. Right? They didn't tell us how much a vending machine weighs. So as we build these equations, we're just going to leave it as W for now. So let's go ahead, and what I'm going to do in this case is actually rotate my x and y coordinates so that my normal force is totally in the y direction and my frictional force is in the x direction, so that really the only guy I'm finding is angles of W. Right? It's going to simplify my equilibrium equations a little bit. I take my equilibrium equation, fx equals 0. I'm going to have W sine 25 minus the friction force. And that's it. So if I solve for f there, I get f is W sine 25. Do my y equilibrium equation is W cosine 25, that's in the negative direction, negative W cosine 25 plus my normal force. So I get a normal force equals W cosine 25. So at this point, you have to recognize, all right, I've kind of worked these equilibriums as far as I can. Taking a moment isn't going to give me really any new information. But again, what I'm finding here is mu. And so we already know a relationship equation for that, which is that the frictional force equals mu times the normal force. So I have a relationship for the frictional force, I have a relationship for the normal force, and I can go ahead and plug those into my equation. Right, so my W sine 25 equals mu times W cosine 25. And we'll notice now that it actually didn't matter that they didn't give us a weight, because it's going to work out. It doesn't actually matter what the weight of this vending machine is. It's not dependent on that. So I can get rid of these W's. They cancel out. Divide that sine 25 over. And I get mu is cosine 25 over sine 25. Or when I punch that into my calculator, that gives me 0.466. And there are no units on our coefficient of friction. It's just a coefficient. It's just a constant value. It's a number. We do not need units on it. This would be our answer. So sometimes these friction equations require you to play around, go integrate in other equations that we already know. The friction equals mu times n in combination with our equilibrium equations to find this mu value. Now that we know how to use statics in our equilibrium equations to solve some of these friction problems, we can really start developing more complex problems and solving them more complex than the ones we were able to do in Physics 1. So, for example, in this example, we have a beam with a distributed load of 200 newtons per meter on it, pinned at one end, and then supported on the other end by this post. And we want to know how much force would be required to pull that post out from under the beam. And we're given these static coefficients of friction as well. So this coefficient of friction at point B, where the post is touching the beam, is going to be 0.2. And then our static coefficient of friction at C, where the beam is touching the floor, is 0.5. So we want to find out how much force exactly is it going to take to yoink this post out from underneath the beam. And there are really a few conditions that might be met to see this. So, like one condition that could be met is that if we look at our post, let's go ahead and break out a free body diagram for the post first. And then we'll talk about these three conditions. So looking at just the post free body diagram, we have that applied force P that we're trying to find. And so then we have the opposing friction forces at C and B, and then the normal forces also experienced. Normal force at B, normal force at C. Up a little, there we go. Normal force at B, normal force at C. This would be our free body diagram for the post itself, not the beam, just breaking out one portion of this system to see these frictional forces. And this post will fall out in one of three ways, right? So one is that both ends are going to slip at the exact same time. So that would be that our friction at B and our friction at C are both in a slip condition. So they're both causing slip. This would be unlikely because you'd need a perfect amount of slip at each point B and C. Whereas what's more likely to happen is one of these other two cases where it starts to slip at B but is rotating now at C. Right? So when B starts to kind of slide and fall off, then C is rotating. And we're going to check for each of these conditions. So B frictional force is slipping, right? Meaning that the actual frictional force at B is exceeding the theoretical maximum. And then there is rotation, at C, or it could be the opposite, that at FC, that's where we're experiencing the slip, and then there is a rotation occurring at B. So basically one end tipping while one end is slipping, or both ends are slipping. Now we can't have both ends tipping because this would mean that it would be kind of bending itself out of place, which would be, I'm not sure if that's physically possible. It might physically be possible, but it would be extremely unlikely. Slip is the most common reason that this thing is going to be sliding out from under the beam. The friction is going to slip and the beam is going to pop out, rather than it trying to rotate itself out of position. So now that we know these conditions, let's go ahead and find our frictional forces. Right, so looking at this, we can already tell that this one portion of our beam, there's way too many unknowns for our equilibrium equations. So we're going to want to go back to our full beam. Right, let's make a quick free body diagram for that full beam. I have an AY, my NB. Notice my NB and my FB are both on my free body diagram for the beam AB, but they're in opposite directions as they were at the post. Alright, so now my friction is flipped directions. I have that distributed load that I'll go ahead and simplify here as 200 times 4 is 800. And then A is a pin, so I do have an AX. Now, even though this form seems to be indeterminate, right, I don't really care about what my AX is. What I'm trying to find here is my normal force at B, so I can take that and put it back into my original free body diagram. So I'm going to go ahead and find my normal force at B. Take a moment about A equals 0. It's going to give me negative 800 times its distance away from A is 2, plus NB times its distance away is 4. So I know my normal force at B is going to be 400 newtons. 400 newtons. And we could see this by symmetry as well, right? We didn't have to take a moment. We could say, okay, this is distributed evenly throughout the beam, so AY and NB are going to be the exact same. By symmetry, they're going to be 400. They each take half of the load. So NB is 400, and I'm going to take that back over to my original free body diagram and write out all the equilibrium equations that I can from this. So I have my NB was 400 newtons, which means that my NC would also be 400 newtons, right? They're the only Y forces applied on this post, so those two are going to be the exact same normal forces. The key with this is that the frictional forces are different between them. So if I use my friction equations, FB equals mu NB, I'm going to have 400 times 0.2. So my FB would be 80. And then my FC in this case, my FC 0.5 times 400 is going to be 200 newtons. So this is the case where they are both slipping. They're both using this mu equals NB equation. There's no tipping. I didn't apply a moment anywhere. This is both slipping, right? These are their theoretical maximums. Both of them are going to be slipping. So if I do my sum of X forces equals 0, I get P minus FB minus FC gives me P is 280 newtons. So this is the first case that we talked about, where both ends are slipping. So you're using their theoretical maximums, because that is the point when slipping occurs, is if it's greater than those maximums. So P equals 280 is one possible load, but we need to check those other two cases. We need to check for the slip at B rotate C case and the slip at C rotate B. Because if those forces are less, if we get a smaller P value for either of those scenarios, it means that they'll happen first. And that would actually be the force required to pull this post out out of the beam, right? Because you don't need to go all the way to 280 if you're already failing at 200. So let's check both of those. And the way we're going to go about checking both of those is by taking a moment. So I want to keep both of these in mind when I'm doing these moments. So FB is 80, FC is 200. And I'm going to go ahead and look at my case of slips at B and rotates at C. So if we're slipping, slip at B, rotate at C. This is the second case we'll look at. So if we're slipping at B, it means that we're meeting this FB equals 80 Newton condition that we found before. But now we're rotating at C, so what that means is we'll want to take a moment about point C. Take a moment about point C and see what P value that gives us. All right, so I take a moment about C. I'm going to get P times 0.25, and that would be a negative. If my counterclockwise is positive, then this is negative. Negative P times 0.25 plus 80 times its distance away from C is 1. So this gives me a P value of 320 newtons, which of course 320 is greater than 280, so this condition will not be met, right? So it's not going to slip at B and rotate at C. Both of them are going to slip before this happens. So let's check our third and last scenario here. And that is our another color, maybe blue. 3 is slip at C, rotate at B. And so in this case, my FC is the one that I'm going to be using. That's the slip condition. And then my rotate at B, I'm going to take a moment about point B to solve for P. So that's going to give me my P times 0.75 is its distance away from B, minus 200 times its distance away is 1, which gives me a P value of 267 newtons. Which we'll notice 267 is in fact less than 280. So my 280 condition is not the condition that is causing the failure, not what's causing the post to be pulled out. Actually, it'll be at this force of P equals 267 newtons, and what's happening there is that we're going to start seeing the slip occur at C. It's going to rotate out at B, and it's going to pop out from under the beam